Hello. So in this mini lecture, we're going to cover some topics that are not strictly necessary in order to complete the projects in this course, but that are going to be very, very helpful. So the two main topics are GetOpt and debugging. But before that, I want to spend a little bit of time just talking through a couple of technicalities that we've been either glossing over or simplifying up to this point. And so I'm going to ask a series of questions, and normally in the classroom I would have I would have a service where you could answer these online as they come up. Since you're watching this in video form, I would just recommend that you pause the video after each question and look at the answers and pick which one you think is correct. I don't expect you to get the questions right at this point. The reason that we're having to talk about these topics is because they are aspects of C which are somewhat counterintuitive. And so, in some sense, getting these questions wrong helps you to remember these technicalities. And so, I would strongly suggest that you play along, even if you are sort of unfortunately doomed to get most of the questions wrong. All right, so the first question is, what do you think that star p.q means in C? This is something that we sort of glossed over earlier. I mentioned in passing. So does this mean we dereference pointer p and then access field q, or does this mean that we dereference the field q of variable p? Or does it mean neither of the above? So take a second to think about which of those you think it means. So one might expect that this would dereference the pointer p and then access field q. This is so if p was a pointer and it was a pointer to a struct, this seems like a reasonable way to say, hey, I want to dereference p and grab the field q. Unfortunately, it actually means to dereference the field q of variable p. And this has something to do with something called precedence. And this is not terribly important in this course, but precedence is the order in which operations are applied. So for instance, 2 plus 3 times 4 means to do the multiplication first, not the addition, even though the multiplication appears later in the expression. And this is because multiplication has higher precedence than an addition. So this is something that you hopefully learned in grade school. And in C, some of the precedence relationships are not quite as intuitive as one might hope. For instance, the member operator is higher than the dereference operator, which causes the behavior that we saw in the question. So star pointer dot foo means grab the foo field of pointer and then dereference it, rather than dereference the pointer, grab the field foo. This is partially why the arrow is such a useful operator, because it allows us to do the thing that we meant to do with the same number of characters. Another place where this kind of trips people up sometimes is that some of the unary operators, so the plus plus, for instance, the increment operator is also higher than dereference. So for instance, if we wanted to increment a thing that we have a pointer to, we might be tempted to write this here, so star pointer plus plus, but this actually means increment the pointer and then dereference that incremented pointer, not, increment the thing that the pointer is pointing to. So if you want to actually increment the thing that you have a pointer to, then you need to use this syntax and put the parentheses in. There's no special operator like there is for the arrow. So that's just something to keep in mind. If you're interested, there is a full precedence list for C at this reference here. All right, so next question. So assuming integers require 4 bytes each and pointers require 8 bytes each, how many bytes will be allocated by the following C code? So take a second and pause the video and see what your estimate would be for how many bytes these variables will take up. Okay, so a totally reasonable approach to this is to say, all right, well, we're going to have this array that has 4 integers in it, and that's going to be 4 times 4, which is 16 bytes. And then we're going to have C and D, which we've spoken up to this point as being pointers themselves, and so that's 2 pointers, and so that's going to be another 16 bytes, so that's a total of 32 bytes. And that's actually not correct. This is only going to allocate 24 bytes. So it's going to allocate the 16 bytes for the array of 4 integers, and then it's going to allocate one other 8-byte variable for the pointer d. And the reason this is happening under the hood is that in C, array names are actually aliases, not pointers, as we've been treating them up to this point. So C is not strictly speaking a pointer here. It's really just an alias for the array in memory, whereas D itself is actually a pointer that in this case is sort of referring to the same array in memory. Practically speaking, array aliases behave like constant pointers, and that's why it's been useful to think of them that way up to this point. And I would encourage you to continue thinking of them as pointers, because in many respects they do behave like pointers. A couple of notable exceptions here is that the address of C, so the address of C here is the address of the first element of C. But of course the address of D is going to be the address of this pointer, not the address of the first element that it is pointing to. So that's one difference. Another difference is that if you use the size of operator on C, you'll get the size of the entire array, whereas if you do size of on D, you'll get the size of the pointer itself. So those are some important distinctions to remember. Another small caveat here is that zero-length arrays, which would be somewhat useless anyway, are generally not allowed in C. So if you try to declare a zero-length array, you typically will get a compiler warning. If you omit the size altogether, it will generally assume that you just want an array of 1 element, which in general is also not terribly useful. But I just wanted to make you aware of that behavior. Okay, so here are a bunch of initializations. So pause the video and think. So 3 of these are integers, 3 of these are characters. And they're just different syntaxes for declaring and initializing an array. So take a look at these and see if you can identify which of these are safe and which are not. Okay, so this is pretty interesting. So your first inclination, hopefully, was that the ones where you're giving an explicit bound, those are going to be safe, and that is true. So here we are explicitly saying we want an array with 4 integers, and here are the integers. So that's safe. We've seen that before. Here we're saying, well, I want an array with 6 of up to 6 characters, and we're initializing it over here. You may look at this and say, well, this is 5 characters, and that still fits in this, because remember, 5 plus the null character, that still fits inside of a 6-character array. So that's fine. The other 2 here that shouldn't feel too worrying are the ones where we don't actually specify a size, but we still specify that it's an array. So here and here. And those are fine too. They operate a similar way, except that it allows, it says to the compiler, I want you to infer how large this array should be. So just, allocate an array, and here are the elements that I want in the array, and just make the array as big as it needs to be. And so presumably you would have some other mechanism for keeping track of how many things you put into that array in order to make sure that you access it safely. So the 2 that are suspect here are C and F. Here, because we're creating a pointer, and we're trying to set that pointer equal to something that's an array. And that should feel off to you. That should feel like something that maybe you're not allowed to do, because, where is this array going? What exactly does it mean to assign an array to a pointer? This should feel a bit off, and in fact this is considered to be unsafe in C, and the reason is that it will take this array and it will try to copy this entire array into this pointer, and the pointer is just a single element, and so this is going to cause a reference outside or past the edge of the pointer itself. And so this is an unsafe thing. So with that knowledge, one might also be tempted to conclude that f is also unsafe because it's doing the exact same thing, except that it's doing it with a string rather than an integer array. And so part of the reason that I wanted to talk about this here is that the behavior here is actually different. This is f is actually safe here as well, and it's somewhat confusing that that's the case in C. So in general, initializing a pointer declaration using an array is going to give you a buffer overrun, and it's something you definitely shouldn't do. However, there is a special case in C for C strings. So if you declare a char pointer and you initialize it to a string constant, what it will do is it will allocate space for that string constant in a special read-only section of the static data region, and it will initialize s to be a pointer to that string in memory, the null-terminated string. One reason that it does this is that it's fairly common for people to use string constants in their code. And if you use the same string constant in multiple places in your code, it's not going to change, and so there's no point in storing multiple copies of it. And so what the compiler will do is it will find all the string constants that are equal to each other, and it will just store one copy of that constant, and it will make all of the pointers that were initialized to that string constant just pointers to that same string constant in memory. So that's the motivation behind this behavior here. But it is a little confusing because it is a special case of something that would generally not be considered safe.